Welcome to Planet Geo, the podcast where we talk about our amazing planet, how it works, and why it matters to you. Okay. Chris.
Jesse.
Mr. Bullheis. Sir. Good sir.
Don't call me that. Don't call me that. It's not been the day for that, Jesse. Hey, hold on. Hey, hold on. The screen share is, I don't like this. Can we do this differently? Like, you're not big enough.
How would you like to do it?
I don't know. But you're like, I can't. This is not.
It's too small
good.
Or what?
Yeah, it's too small.
Try pinning it. Try pin to my screen. Will that make it bigger for you?
There you go. There we go. That's
good?
Better. Good,
Okay.
Good deal. All right. Okay.
Now we can proceed.
We can proceed. How we doing, Jess?
That was a close one right there, Chris. We almost had technical difficulties. We got out of it, though.
We did. We did.
Okay, well, on this episode of the Chris Bullheis Experience, we are going to talk... Oh, no, that's not the show name. This is Planet Geo.
You do get real Chris today, though. You know,
I do get real. Yeah, I always get real Chris, and but I'd rather have real Chris than anybody else out there. So that's good.
Well, good,
Chris, we get to talk. We're talking about real badass rock today. Like this is a cool rock, a famous category of rocks. If you're a rock collector, you know this word. But before we get to that, Chris, you polled your students. You had homework, and I think you've accomplished that, right? You're going to change the name of your course from geology to geoscience. And your homework was to, like, I forget what it was, actually. Ask them what they thought about it.
Yeah, it was, what were their thoughts? You just said poll them. I want to know what they think.
And what happened? What'd you ask them and what'd they say?
So I changed my class for the last 25 years has been called geology. And through our discussions with Rachel Phillips, Geo Girl, and so on, I decided, and plus with you and just doing this podcast, we never really refer to this as geology. We've called this geoscience, and so I'm like, I just put a bug in my ear. Wait a minute, maybe I should change my class to geoscience. And so I thought about it. We talked about it. I did it. I went and changed. It was remarkably easy, but I've
okay, that's good.
So I've gotten questions from people that actually noticed that my class is now changed from geology to geoscience. I'm getting emails from counselors about questions from students and things. So I polled my current geology classes, my beloved, I love them.
Yeah. So these are juniors and seniors in high school?
Yes.
The mix between the two? Okay.
Yep. And they're so good. And so I said, I want to know what you think. And so I wrote on one side of the board, I wrote geology. On the other side of the board, I wrote geoscience. I said, if you read these, or if you were thinking about course offerings and these were your choices, how do they hit you? Do you think about it differently, geology versus geoscience? So I just kind of let it sit for a few seconds. And then I'm like, what do you think? And I had a couple of camps.
Oh, interesting. Okay.
Yeah. Some of my students, they thought that geoscience seemed to be more difficult in terms of just the rigor of the class. Yeah, that caught me by surprise.
That's really interesting. Huh.
Yeah. They thought geology would be just, kind of a rocks for jocks kind of thing. And whereas geoscience seemed maybe a little more of a reach.
Interesting. Okay. So sort of more quantitative, more difficult, harder class, basically. Oh, that's interesting.
Now,
okay.
That was not the majority. I would say the majority of my students felt that geoscience was a better term for my course because we don't just do geology. We don't just do hard rock geology and some soft rock geology and call it that. I mean, we talk about resources. We talk about climate and climate change. Whenever I can, I bring in planetary because I like to, cross that with my astronomy classes and so on. And so a lot of my students thought that geoscience had a broader umbrella. That's bigger, really more inclusive umbrella. Yeah.
Well, I mean, okay. So that's really interesting that they've plugged into that as a junior in high school, having basically no exposure to the field, the discipline, the industry is involved. I mean, it's really interesting that they just kind of, because that's the point, right? That's the point of everybody rebranding as geoscience or even earth and planetary science as more of a broader envelope, even beyond geoscience. So
that's right.
I'm really impressed.
The intent,
that's very impressive.
Right?
Yeah.
Yeah. And some of the questions that the counselors have passed on to me affirm that thought.
Really? Okay. Wow. So the counselors are getting questions about, or asking you questions, sort of, how do we advise students about this class, college preparedness, all those kind of questions. Okay. That's so interesting that a little slight rebranding change. I mean, nothing's going to change in the course content. It's just a name change. And
yeah, but so this is really interesting though. I mean, we struggle with this, right, in our field. And I had a professor, one of the geoscience professors at Michigan Tech, he emailed me a few weeks ago and said, I want to come downstate. Now that's no small thing. That's like a 9-hour drive, right?
That's a long ways. Yeah.
And he said, I want to come downstate. I want to meet your classes. I want to see your classroom. I want to meet you. I want to talk to your classes about, and this is really cool, careers in geoscience.
Oh, that's amazing.
And,
okay, cool.
And then he's like, and then also, if it would be okay with you, I would like to plug Tech, Michigan Tech, because we have it going on. I'm proud of where I this is my alma mater. I love this place. We do the best job, and
that's
your
so
kids
cool.
need to give us consideration. And it was so cool. So he came in yesterday actually and talked to my classes, and
really cool.
It's like I just loved the hustle of it.
Yeah.
To be honest with you.
Totally.
Here's a university that's
come down and kind of recruit in a way. Hey, what am I doing here?
An event.
Come on, I got to come to Hudsonville and do the exact same thing.
You absolutely do. I would so love that. But,
absolutely.
So I thought this guy came down because Michigan Tech had an event last night. And I'm talking to him in between classes because he stuck around. I have, my first hour, then I have an off hour, and then I have my third hour. So he had like a window of 2 hours. So I'm asking him, like, are you here for that? He's like, actually, no, I wasn't even invited to that event. I came here to see you.
No kidding.
And I'm like, no kidding.
That's interesting. I mean, this really is the way. I think that's such a good. Well, okay, he's doing a good job. He's doing it right, and conveying what the career opportunities are. That's very cool. And recruiting too. I mean, we need to recruit. Every university out there needs to recruit at the moment hard. And that's a good thing. Wow, that's super interesting, Chris. I want to talk more about this, and I want to come to your class and tell them about,
I would love to have
State is.
And that.
I'm actually giving a talk at a local college in a couple weeks, and one half of the talk will be kind of science. It's big. It's one of these big public, talks, alumni supported. So it's an evening lecture. Anybody from the public can come. So it'll be half science and then half I firmly believe, and a lot of our people we interview have conveyed this, it is a good time to be a geoscientist or even more a geologist. It is a good time to be in this space. And I want to kind of convey that in a talk with some data and with some kind of theories about why that is. So,
I know we got to jump into this real quick, but I'm sorry to interrupt. But he, as this professor from Michigan Tech was talking to my classes, he pointed at me during this lecture, not a lecture, but talk, and he said, and one of your counselors advised one of your students a few years ago to not go into geologic engineering. And he said, I don't know his name, but this other professor, Dr. Luke Bowman, will know. And so he said, you need to tell that counselor that he's now working in Alaska and he's making 150 G's. So,
so there you go. Yeah.
So I found out exactly who the counselor was. I know who the student was. I figured it all out. So
that's funny.
I have to talk.
Oh, that's super interesting. All right, well, 10 minutes into this episode on Puddingstone, we're finally getting to it, but that's all very interesting. And the geoscience, this is a very exciting space. And we're going to have a bunch of interviews kind of conveying this. I mean, Richard Alley are about to record I mean, what's the title of his talk? Get Rich and Save the World. I mean, that's the title of his talk. It's an amazing pitch for exactly what we're talking about here. So anyways.
All right. Can we
Chris,
go? This is my idea, so I'm going to lead it off, okay?
Yeah. What are we doing?
All right. We're talking about, well, you call it, I mean, I guess it's called Puddingstone. I like to call it Puddingstone. It's a little, it's a little, yeah, notice it's a Michigander twist on this. It's like,
of course you like to call it Puddingstone.
I don't say pumpkin. I just like to say pumpkin,
Yeah.
This is we're going to talk about Puddingstone today.
So Chris, hold on. Just for when I'm writing the title, I need to take the G out and put an apostrophe in. Is that what needs to happen here for this one?
Yes, please. Okay. Please do. Right. Please do. So
that's super funny.
Puddingstone is a type of conglomerate. And the term it's a special kind of conglomerate. We're going to get into that, but it's a term that comes from a conglomerate that resembles like traditional plum pudding or fruit pudding. Okay. So in other words, it's this kind of cakey material that has fruit globs in it. And that's how Puddingstone gets its name, because it resembles that.
Exactly, Chris. And the key here, and we're going to show a bunch of photos. We've got some photos showing of a variety of very
throw
famous.
One up. Let's go.
Well, here we go. Okay, so this one, there's three main ones we're going to highlight that we have pulled some photos from our own collections and from the web here. But the key here for most pudding stones or put-in stones is we differentiate sediments, especially when they have big clasts in them, as either clast supported or matrix supported. And those terms, I think, should make sense if you kind of think about it a minute. Like, what's structurally valuable to this rock? Is it the clasts and then the matrix fills in the extra space? Or is the matrix fundamentally the structural thing holding it together? And in most pudding stones, it's a matrix supported conglomerate. So that the pudding pieces or the plums in their plum, I don't know, what's the plums here?
It's like a fruit pudding or plum pudding. It's all, the
fruit pieces,
I think it's an English term,
are not touching each other. They're floating around in a sea of matrix. And this first photo kind of shows us very few of the grains are actually touching each other here. And we can skip ahead even more to see something like this one. We'll move down in the end, but this famous conglomerate later on in Michigan, where the matrix is the structure and the plums are just floating in it. I think
that's such a good point, but it's such an interesting take because it's true. What you said is true. It's matrix supported, but the beauty of a pudding stone are the clasts. Okay.
Oh yeah. Oh, it's the whole game.
And so, So in order for it to be a pudding stone, the clasts have to be like, this is kind of a general unwritten rule, I think, is that the clasts are of very contrasting color. They are very different from the matrix that supports them.
That's right. So, and they're usually,
focus,
very rounded as well. Most pudding stones.
No, look,
that's too much.
Pudding. It's pudding.
Okay. Most pudding stones have very rounded clasts as well. So these are well-rounded conglomerates. This first example here, this photo we're showing here from the Hertfordshire Puddingstone in England is very rounded. These are very rounded, very few sharp edges on the clasts, right? So that's another
and
piece
so
to puddingstone.
Just from a geologic standpoint, what that means is, so first of all, it's conglomerate. The clasts are big. These are gravel sized to bigger sized pieces. And that is indicative of the depositional environment then. So these were high energy sedimentary deposits, like a fluvial deposit that was like a fast moving mountain stream kind of thing, high energy shoreline possibly, but because of the big class high energy. And then the rounding is indicative of the degree of transport, the degree of erosion that took place. And this was a significant amount of erosion, just simply because as these things are transported downstream, every impact they make, it just rounds it off further and further and further. And so that's just typical conglomerate stuff. But the thing is, first of all, Jesse, what are some examples of the clasts? We touched on it a little bit, but let's do that. right?
What
are the clasts?
Yeah, the clasts can be a wide variety, and the three different rocks we'll go through here, three different types of puddingstone, will have different clasts in them. So some of them are chert clasts, really the famous ones that from when we grew up in Michigan.
What's
famous
chert?
puddingstone. This would be pure silica jasper chemical
sediment, like a microcrystalline
bright red. Yeah. Some of the class will be quartzite. Out here in eastern Pennsylvania, we have conglomerates, these pudding stones that have basically pure white quartzite as the clast material itself. And then other ones will have little volcanic rocks, volcanic or igneous rocks that are the clast. So the clast can be a lot of different compositions. And that's really powerful because if we have a rock that's made up of clasts of other rocks, and you said a fluvial environment, which is a river environment. This is a kind of a river system. Think of like a channel bar or a channel cut where there's gravel in the bottom there, and then that gets covered over by sand later on. That can be a formation setting for puddingstone. But by looking at the clasts, we can tell what was that river eroding? What was the catchment or the river drainage basin? What was the geology or the makeup of that drainage basin? Was it a huge drainage basin or a really small one? So we can study the clasts and therefore study the actually erosional surface back when this sediment was deposited, when this puddingstone
In other words,
you're
talking like we can sometimes point to the source area. Where did these pieces are distinctive enough oftentimes where they come from a very specific, precise location, which I think is a really cool aspect to conglomerate,
Yeah. And again, or alter, that's one example. Another example is, let's say, you've got one class that's one age, another one that's a totally different age from a totally different geological province. It means that river, that the basin that was draining into that river system was huge, right? So you can both tell like where the sediment was coming from, where these clasts were derived from, but also how big was the river's drainage basin, which is a really cool feature of these conglomerates.
So here's a rule. All pudding stones are conglomerate. Not all conglomerate is puddingstone.
Yeah,
right.
Well, nicely said.
It's just this general thing, and what we're looking for is these classed, the matrix supported clasts that have really contrasting colors to that matrix, and it makes it resemble, and it does. I mean, if you Google image fruit pudding, you get these. It looks just like it, and it's so cool. So,
and
it's
the other rule,
special kind of conglomerate.
Yeah, the other rule is they have to be kind of beautiful. And most conglomerates are pretty beautiful,
right.
But these ones are like spectacularly pretty with the contrasting colors as you're describing them, right? So we can do a lot scientifically with these pudding stones, and they have served many different purposes, and it depends which pudding stone we're talking about, and we'll work through three of them here. But we can do things like reconstruct past river systems. We've talked about that. Climate conditions, we're going to touch on that with the last pudding stone, the one that's exposed in around the Michigan area. Talk about ancient climate conditions. We can use these rocks because they're deposited in like a river setting, a riverine setting, and so that is very intimately connected to climate at that time.
Something else to think about. I'm just going to pose it as a question, then we'll talk about this, right? But how maybe would puddingstone, because I can see it bothers you when I say it every time. Your doctoriness is cringy.
No, it's just it's like positive. I'm not confident I'm going to say it right, so I don't want to butcher it. So I'll stick
positive.
With what I know.
It's not positive. Like a dog's paw.
Case in point, Chris. Case in point. Right. I'm just going to botch it. So I'll stick with what I know. Thank you very much.
How might puddingstone be related to plate tectonics, to tectonic activity and tectonic uplift? That's one of the geologic significances of puddingstone, is that it is tied to that, because it may indicate this like extensive mountain building event that provided ample sediment then to get carried away and then later deposited. And we can tie those clasts back to that mountain building event. So
Chris,
it's important from that standpoint.
Let's think about this, because a pudding stone just has a kind of, it's a little bit counterintuitive. And here's the reason. You have large cobbles or large clasts, which those are heavy. So those are not easy to transport. Right? Those require high energy, river to transport those things. But they're also very well rounded, which means they had to be transported kind of far. And so you need to have high energy and far transport to get big cobbles that are well rounded. And that means something pretty peculiar or pretty let's say, unique about the depositional setting. So high mountain ranges, where there's a lot of, the river is cascading down thousands of feet of mountains, is a good way to do that. So
that's right.
Anyway, scientifically, that's what we can do. And then we already touched on the provenance. We can look at the class, so we can study the individual
explain
fragments.
what you mean by, so provenance means the source, right? That's your fancy term for, where did they come from? That's how I would say.
Stick my finger up in the air while we're talking.
Yeah, you do.
Provenance.
Yeah. Well, Jesse, let's just get into then some really exceptional examples of puddingstone. And we'll end with my favorite, of course, because it comes from my beloved state of Michigan.
No, my favorite too, because you and I, we grew up, we've spent ample time looking in gravel pits in Michigan for puddingstone. All right, we're going to start with one called the Hertfordshire puddingstone from England, from the UK. This is a silicified conglomerate. So it has,
what does that mean?
It had silica enriched. So it's had silica flushed through this rock. And silica, which makes up quartz, is easily dissolved in fluids. And so if you can dissolve it in fluids, you can flush it through rocks that have porosity, permeability, and you can pass fluids through them. So sediments, you can flush it through with silica.
Let's talk about that a second, though, because silica actually is not easily dissolved. Not at least in terms of a common cementing agent or, that kind of thing that binds it together. This might be indicative of something special, right, Jesse?
Yeah. Well, you need to have pretty high temperature fluid. I mean, we're not talking about like ocean water, at least modern ocean water. We're talking about relatively high temperature fluids that you will get sort of in the crust, not surface waters, really. So yeah, that's a really good point.
Again, points back to the geologic significance of what you have in this rock,
Right.
Yeah, water is a powerful solvent, but hot water is even more powerful as a solvent, especially if it's hot and salty.
Exactly. And in this rock, this image we're looking at here, you can go again to our Camp Geo app and see the visual podcast version of this. Also on YouTube, you can see this as well. But basically, all these cobbles, or all these clasts, many of them at least, have this dark rim on them, this dark rind, which is silicification kind of front. So this is the silica flowing through the matrix. It's easier to flow through the matrix. And it has a hard time getting into the cobbles, so it makes these beautiful concentric rings around these cobbles. And, it's driving different reactions in different cobbles, but it's all
just for reference to when you're referring to the matrix, you're referring to the finer grained, basically the cement that is supporting these big clasts, right?
Yeah, thanks. Yeah, that's exactly
the
right.
matrix. So
that's exactly right. And
so
here,
Chris, this Hertfordshire has mystical powers, Jesse.
Rumor has it, it's mystical powers. Actually, we've referred to this in an old podcast episode. I don't actually remember. I was trying to remember where we referred to this, but this was a rock that was thought to procreate because you can imagine why, right? You've got this conglomerate.
Wasn't that Devil's Tower?
Was it Devil's Tower episode?
Devil's Tower grew. I mean,
well, no, we referred to this particular puddingstone.
Oh, did we? Okay.
And we referred to the ancient lore that this would come up in fields, like seasonally. These puddingstones would kind of come up in fields. If you look at this rock, it looks like you have a bunch of baby rocks inside the rock, and then this rock is kind of being birthed from the ground. So you can imagine how this lore starts, that like this rock is procreating down in the earth and forming more of itself, and it's coming to the surface, and every year we have to freaking get it out of our fields so we can grow potatoes or whatever the heck is grown in Hertfordshire. Sorry if anybody's from there and I'm getting the crop wrong, but
it's such no, don't worry, it is such a pretty rock. Like I love this rock is a pretty amazing rock.
And there's a lot of varieties of it. For me personally, this one on the right here, we're talking, this is gray cobbles with these dark rims and this kind of gray matrix. Stunningly beautiful. This is a exceptionally beautiful rock. I love this rock. Yeah. So I don't know. That's kind of the Hertfordshire one, that silicified. And I've seen countertop material, Chris. Actually, one of my collaborators who works in the Northwest Territories has this countertop material. It's not this rock. It's a similar one, a silicified conglomerate that has, I think it came from Brazil, maybe. I don't remember the name of it. But when you cut and polish this stuff, man, is it spectacularly beautiful.
It reminds me so much of the terrazzo floors in my hallways at school.
Oh, yeah, like the sort of fake concrete with the little flex in it and stuff.
It looks a lot like that. It
That's
really
a good
does.
point. Yeah, so, totally. Okay, Chris, number 2.
The Roxbury conglomerate,
Roxbury,
Massachusetts. We've been here. We've collected here.
We have.
That's right.
Not here in this photo, but this is a photo from Gettysburg. We have not collected at Gettysburg. This is just
gosh. But sacred place.
We've both been to Gettysburg separately. And actually, we've been working on putting together a Geology of the Battle of Gettysburg episode, which will be very exciting. It's just taking a long time to kind of wrap our heads around exactly what we want to say about it. But this is a photo, this is an image of a big monument, this is a huge block of conglomerate that was shipped down from Massachusetts in honor of the 20th Massachusetts Infantry and is on the field at Gettysburg there.
I'm trying to remember where, so it's July 3rd. Is it Pickett's Charge? I don't know where this is. Honestly,
I'm not. That's a good question.
Familiar with the battlefield of Gettysburg. I've been there so many times, but I don't recall this monument, and I have to fix that. That's a shame.
Well, look it up and report back.
I will absolutely. Yeah. So that's interesting. This is the official rock of Massachusetts.
Yes, interesting, right? A Puddingstone is the official rock of Massachusetts. I'm not sure how
renamed it. That's right.
The New Englandites would appreciate it being pronounced Puddingstone, but whatever. Chris, this rock, what is the state rock of Michigan? I don't actually know that. Do you know?
Petoskey.
Of course. Stone. Oh, that's obvious. Yeah, duh.
Yeah.
Okay.
Yeah.
Right.
Yeah. Petoskey is a type of coral organism. It's really pretty. It's known for this kind of honeycomb look to it. It's pretty amazing.
Very beautiful. And I just had to look this up a minute, but Pennsylvania does not have a state stone, apparently.
Oh,
interesting.
Okay. Right.
No state stone. We might have to go about changing that.
That needs to be fixed, Dr. Rydick.
No state stone, no state mineral. What the heck?
No.
It's
and
crazy.
You guys have great rocks. You have great
rocks. And we have a great and long history of geology. It's crazy. What are we doing over here? We got to get it together.
This needs to be taken care of. So coming out of State College in the near future, State Rock for Pennsylvania. So,
maybe this will be my platform for running for office in Pennsylvania.
Please don't ever do that. Please don't.
That's not.
I cherish you as a friend, and we might have to part ways if you become a politician. So
no. You can come stump for me. That's what you done to do.
That's true.
So back to the Roxbury conglomerate. So this is a 590 million year, somewhere in that ballpark. The breakup of a supercontinent is really what's happening here on the eastern seaboard, pre-Appalachians, the breakup of the supercontinent, big rift basins forming, big river systems, ancient river deposits dumped in this Roxbury conglomerate. And this, if you could see a photo, there's science museums in Boston, at universities in Massachusetts and in New England who have slabs of this. It's a very common building stone in the Boston area. It's spectacular. Bright red cobbles, green cobbles, set in a kind of a greenish matrix. It's really, really beautiful. And Chris, I'm going to skip ahead here a photo. These ages of rocks, the conglomerates like this occur all up and down the eastern seaboard. There are different basins that formed in this 530 to 580 million year interval that are in the what's called Piedmont area, and is sort of you get east of the Appalachians. There's a whole bunch of these old basins that dumped around that time, 530, 580 million years ago, formed conglomerates. And this is a photo of a conglomerate that I collected in York, Pennsylvania, where we used to live. And this is a big bookend. I mean, it doesn't really look like it, but it's like 1.5 feet tall.
It does.
With big, pure quartzite cobbles in there. Bright white cobbles in a really green chlorite-rich matrix. So it's been metamorphosed to get that green color.
I was going to ask you about that. And also, too, Jesse, these quartzite clasts are not very well-rounded.
No.
At least some of them,
And it's actually class supported, so it's not technically a pudding stone, but this is just to show that, like, these kind of extensional environments create a lot of rocks like this, and all up and down the eastern seaboard you can find outcrops of this stuff. So the Roxbury conglomerate is one of them, and that the Roxbury pudding stone, another name for it, very famous pudding stone.
Okay.
So Chris.
Well, Jesse, can we get to the big show now?
let's get to the show.
And I'm not talking about me. I'm talking about the rock. Okay, the rock.
I do see that the guns are out today with the short sleeve shirt on, despite it being freezing cold in Michigan. I'm sure right now.
Yeah, but I'm warm and toasty in my house. So
yeah. Okay.
So yeah, let's go to the Lorraine Quartzite Puddingstone.
Oh man,
which I think is the Michigan. It's the Ontario, Canada. But it's the Michigan Puddingstone, if I'm going to be quite honest with you.
Well, and here's why, Chris. Let me just say why that is. This rock is exposed in the bedrock in Ontario, so right across Lake Huron from Lake Michigan. It's kind of the northeast side of Lake Huron. There's exposures of it. And what that means for Michigan is that this rock is everywhere in Michigan, because as the glaciers scraped down, they were kind of coming into Michigan area, kind of straight down to the south or down to the southwest, scraping across that direction. So this conglomerate, this rock, has been broken up by the glaciers and deposited all over Michigan. You can usually, if you find a cobbly beach on the Michigan side of Lake Michigan, on the east side of Lake Michigan, you can usually find a piece of this conglomerate, because it's that common in the glacial till and the glacial kitty litter that is all over Michigan.
And it's common too in gravel pits. I mean, it's super common. You can find, super common, you can find it in gravel pits, and you can find like fist-sized pieces up to really, really big size,
house-sized pieces.
Spectacular,
if the owners and operators of the gravel pit have half a brain in their head, and you drive past the gravel pit, you'll usually see a big piece of this like sitting out like gate posts, because they've recognized this is a really cool rock. We got to go put that out front of our building or of our parking lot or of the entrance to the gravel pit. So it's you and I, Chris, we've gone fishing in a lot of gravel pits for rocks, for this rock. Exactly. And we've gotten some, I've got a beautiful monster piece that I've drug all over everywhere I've moved. It's sitting in my yard right now from those gravel pits. So
I call it the Big Show because to me, it's the prettiest. I love this picture that you have up there right now.
I mean, there's no doubt. And let's zoom in the next one here, Chris. Let's zoom in on this. There's no doubt. This is a stunningly beautiful rock.
And what makes it so stunning is the contrast. You have this really light colored white to light gray quartzite matrix. So this is a meta conglomerate. It was a sandstone that was the matrix supporting these, what are the jasper clasts, these beautiful red clasts in it. And then it got metamorphosed. We'll talk about that in a second. But so I call it the Big Show because it is, to me, the most beautiful. And also it's 2.3 billion years old. I mean, this is a very, I don't know, like that's impressive. It's such an old, cool, beautiful rock. So it is the Big Show of the Puddingstones to me.
Chris, there is a big scientific story that this rock tells too. First of all, I want to touch on a couple things. The red class, beautiful jasper, kind of jasper nodules in here, very red. This photo, we're zooming in a little bit here, so you can see a couple big red clasts, a lot of big white clasts, and then this white sandy matrix, this ultra clean sandy matrix. There's a really cool story in this rock and in this kind of the outcrop or the series of rocks that these conglomerates are exposed in. First, I want to go back to this photo where we're showing this is really a conglomerate lens in a sandstone, right? It's not hundreds of meters of conglomerate with jasper in it. It's little lenses that are conglomerate rich with quartzite, more around it. Sandstone is much more common in this Lorraine group or Lorraine formation. But the scientific story here is really cool. This is part of a package of rocks that's a really famous package of rocks called the Huronian supergroup. And these things are like 2.4 to 2.3, 2.2 billion years old. And they contain a record of a really interesting geological history of probably snowball Earth events, like global ice age events, and really a climate that was oscillating wildly between an ice planet and a greenhouse planet, an ice house planet and a greenhouse planet. Like right now we have this, we've talked about the greenhouse effect and climate dynamics, and we have a climate that oscillates back and forth, and there's some thermostat regulator on that. And back in time, that regulation might have been way off. And so it's going glaciers everywhere, no glaciers anywhere, glaciers everywhere, no glaciers anywhere, something like that. And this particular rock from the base of that Huronian supergroup sequence to the top where this Lorraine Quartzite sits, shows a record of no oxygen in the atmosphere at the base, to these rocks contain a record of oxygen in the atmosphere. So the first time that Earth got oxygen, free oxygen, O2, in the atmosphere, called the Great Oxygenation Event, was around this time, 2.3 billion years ago. And the evidence, some of the evidence, comes from this rock where we have quartz crystals. The little quartz crystals in the sandstone have little hematite coatings around them, little red hematite coatings. You could kind of see it in this photo, just a little hints of it.
Now, can I interrupt, Jesse? Is that because the hematite can't precipitate unless there's oxygen present?
Beautiful.
Because
absolutely,
is that right?
Yep,
okay, so
that's exactly right.
If you can have iron dissolved in water all you want, you can saturate it with iron, but it stays in that form unless there's oxygen present. Then it can precipitate, which that forms the iron oxide, the mineral hematite, which is one of my favorite minerals, by the way.
Yeah, I mean, hematite is a really oxidized form of iron. There's more oxygen in that mineral than there is magnetite, for instance, which is iron and oxygen, but a different proportion of that. And at the bottom of this sequence, so at the bottom of the Huronian supergroup, you have rocks with detrital pyrite in it and detrital uraninite, which we'll talk about these in later episodes when we talk about this great oxidation event. But basically, those minerals cannot survive if there's free oxygen in the atmosphere. They'll create sulfuric acid. They'll create acid mine drainage, what we call acid mine drainage. If you take pyrite and expose it to the modern atmosphere with loads of oxygen, it creates sulfuric acid and acid mine drainage right now. It's a really interesting story. It's a absolutely beautiful rock. I love this rock.
I want to, maybe this is a prelude to another episode then, because that was super interesting. You got really doctory on me there, because all I was going to say is this is a conglomerate that got metamorphosed. It got buried really deep. But I have a story about this that to me that is relatable, I think, because I think a lot of our listeners do a fair amount of traveling and exploring in the Western United States, for instance. So this conglomerate with all of the jasper and these rounded jasper clasts surrounded in a matrix of quartzite because of metamorphism, this kind of low grade but confining pressure metamorphism. So you don't get foliation, you don't get this alignment, is very similar to what we find in Glacier National Park, which in the surrounding areas, which is this mud chip breccia rock.
Oh,
it's identical
I remember
to
seeing
this.
Yeah.
Yeah. So what you have are these red oxidized iron-rich mud chips that during storm events, the mud chips would get ripped up and carried in this sand and deposited then. And the only sorting you get is just really rapid deposition. And then it got buried and metamorphosed into this kind of mud chip breccia. It's a meta breccia rock. It's spectacular. It's such a cool story. But it looks identical to our conglomerate here, minus the rounded class. They're all angular.
Okay.
Yeah. It's such a cool thing,
I mean, the stories, I just love these rocks. The stories that these rocks tell. The stories
of rocks are amazing,
It's amazing. And I study, you and I love the hard rocks. We love the igneous and metamorphic rocks, right? The story in those rocks is amazing. It's a little harder to look at and extract the story out of those types of rocks. You look at something like this puddingstone here, and you say, oh, there used to be jasper exposed on the surface of the earth, and that got eroded and deposited in this ancient stream bed. You can stand on the outcrop, explain that story, and it just hits you in the face. It just says, oh, okay, I get it. That's amazing. So sediments have this beautiful, they are very good at exposing this very descriptive storytelling that rocks contain. So I love sediments for that, for that fact.
Well, I want to wrap up this segment here by just saying that these rocks were brought to Michigan from Canada about 24,000 years ago from the Laurentide ice sheet. But I want to, we just need to make this quick, Jesse. So I'm going to limit you on this. You got a short leash. But how can we say that the original rock was 2.3 billion years old? Do you have can you do that in a quick way?
So there's a couple different ways. The most reliable way is to date ash fall deposits that are in with the sediments. So in this huge sequence of the Huronian supergroup, there are ash deposits that are embedded in the sequence. If you don't have ash in the sequence, so if there's ash fall, we can extract zircons from that and date those zircons and say, okay, we know when that volcano erupted, plus or minus 50,000 years, which is plenty of age resolution for this time. If we don't have that, you have to go back to some really basic first principle geology. What's the rock that the lowest sediment is sitting on?
Cross-cutting relations and things
cross-cutting
like
relations,
this, right?
Yep. And exactly, that's where we get the 2.2 number. So the top of this sequence, that 2.3, 2.2 number is a little bit, well, it depends which sequence we're talking about here, but there are some cross-cutting dikes that are dated around 2.15. So that provides a minimum. That's
so cool. So even here, we have multiple tools in our box that we're using to date the big show of Puddingstone conglomerates,
That's exactly right.
So that's pretty awesome.
When we're looking at a rock like this, we can provide a maximum depositional age on it too. We could say, what is the oldest this rock could be? And that's by looking at the class in there and looking at any minerals in that rock, because any minerals in that rock had to form before the rock itself. It's principle of inclusions is what we call that. So if I date zircons in the conglomerate, the youngest zircon has to be older than the age of the rock. So the youngest zircon is the maximum depositional age. It provides an upper bound on the age of this conglomerate by, doing that kind of basic geochronology. So you're right. It's we have loads of tools to tell these stories with, or tease apart the story.
And also, just to reiterate, we've covered this before, but it never hurts to cover this ground again, is that dating sedimentary rocks, which I know this is metamorphic, but the original rock was sedimentary, is exceedingly difficult because you're dealing with clasts that got weathered and eroded out of another rock that formed at a different time. So it doesn't give you the time of deposition. It gives you the time of formation from the parent rock that kind of gave birth to the clasts that became this rock. So it's tough. And, we've covered this in detail before, but it never, like I said, it never hurts to cover ground again, I think.
I mean, it never gets old, too, talking about geochronology and beautiful rocks. The last thing, Chris, I'll note here about Puddingstone, this is a photo of a Puddingstone rock that I have cut. I mean, I mentioned this before on the podcast, but we have this little Etsy store that we cut rocks, and I haven't done much recently with it because we've been moving and my rock saws have been defunct, but decommissioned for a little bit until I get the correct power out to the garage or whatever. But this, just go to like Etsy or go to some rock collector's website and type in Puddingstone, because there's a lot of the rocks that we've talked about. The three that we've talked about are pretty common in those search results, and it's a very, very, very common rock. Could spend a lot of money buying yourself a Puddingstone piece on rock collector websites. It was surprising to me how popular these things are in the kind of rock selling markets, these Puddingstones, because they're really beautiful, really popular. And this is not a spectacular photo of the Puddingstone.
Well, yeah. So that brings up an interesting point, Jesse, is that I sent you like 3 pictures today. Not one. Listen, everybody. Not one of my pictures made the cut. Okay, I sent Jesse pictures of Chris Bullheis Puddingstone, and none of them made the cut here today. So,
Chris, if you'd send me photos of rocks bigger than your thumbnail, it'd be nice. Then they might get shown here.
Please. Oh my gosh.
Here's what I want. Send me a photo of that. I know you have that big giant one sitting in your backyard, probably.
It's covered in snow right now. It's 2 feet of snow outside right now, Jesse. I'm not going to go and pour water over it to uncover it. Sorry. It's not going to happen.
I'm just your commitment level, Chris. I'm constantly disappointed by your lack of commitment to good, images for this podcast. What the heck, man?
Right. That's unfortunate. I sent you good pictures, and you just you're getting a little too arrogant, Jesse. You tone it down a little bit.
That's not news.
That's not true. True statement. All right.
That's well,
a wrap,
Chris,
Jess.
let's summarize here for us, like real quick here, right? Puddingstone, beautiful rocks, Puddingstone, if you want to pronounce it that way. Lots of different varieties. We touched on 3: Hertfordshire Puddingstone from the UK, the Roxbury conglomerate from Massachusetts, and the Lorraine Quartzite Puddingstone. And these rocks, they're just spectacular. These are one of the cooler rocks that's out there. If you're going to study sediments, it might as well be a conglomerate, is kind of the way I think about it. And if you're going to go spend your time collecting sedimentary rocks, it might as well be a Puddingstone because they're beautiful.
That's a good point. They are. Yeah, absolutely.
Hey, that's a wrap. You can follow us on all social medias at Planet Geocast. You can follow us on YouTube now. We have a YouTube channel. You can find that on our website, the Planet Geo Podcast. And head to our Camp Geo mobile app. First link in your show notes. There we have visual podcast series about a whole bunch of things. Yellowstone National Park, Grand Tetons, Grand Canyon, Earth's climate, Earth's oldest rocks. A lot of series that we've been building in the background.
Got a lot.
Download that. Lots of fun stuff there. And we're just continuing to put more. This episode will be there as well, so you could see the images under the Planet Geo tag there in the visual podcast series. So check that out and let us know what you think.
Right on. Cheers.
Peace.